We present OptiState, state estimation of legged robots using gated networks with transformer-based vision and Kalman filtering. State estimation for legged robots is difficult because dynamic motion produced by footsteps can cause motion blur, making vision data less reliable. And due to constantly making and breaking contact, along with slipping, kinematic information can be error-prone as well. Our solution is to employ a hybrid approach, consisting of model-based Kalman filtering so we can employ domain knowledge, optimization for improved robustness, and learning methods to correct for nonlinear errors. We have sensor measurements using a depth camera, IMU, and joint encoders. These measurements are used as input to our Kalman filter. We have a MPC which takes as input the reference trajectory and outputs ground reaction forces to follow this reference. These forces are then sent as input to the model equation of the Kalman filter. The output of our Kalman filter along with other variables shown here are sent as input to the GRU. We use a vision transformer to convert a depth image into a smaller latent space, which is also used as input to the GRU. The GRU then provides the state estimation and associated uncertainty. This is the simplified version of the flowchart. Here we evaluate the autoencoder after training. The output image is the reconstructed depth image after being encoded into a smaller latent space. We now show the GRU data collection process. We have a depth camera that is angled about 45 degrees to the ground, a 6-axis IMU, a motion capture system to measure the ground truth, and a T265 camera which runs VIO SLAM and is used for our baseline studies. We now show the GRU data collection process, starting with motion on flat terrain. To validate the estimation on slippery terrain, we put socks on the robot's feet. To further add disturbance, we occasionally pull on the robot and increase the amount of slipping. To evaluate larger change in robot's z-axis height, we made the robot walk on an inclined terrain. To evaluate rough terrain, we placed solid bouldering holes across the environment. We also placed foam shapes, which are highly compliant. Here we show the evaluation on a trajectory online. We ran several state estimators at the same time, which include our own OptiState in blue, using just our Kalman filter in green, VO SLAM baseline in magenta, and ground truth in red. Note for our MPC controller to track the reference, we used the current estimate from our own OptiState to validate that we can run our estimator online. From the results, we observed that VO SLAM showed good performance at tracking position, but struggled with velocities. The opposite case being true for the Kalman filter. OptiState was able to outperform our baseline for all states as it closely followed the values from the ground truth. Thank you for listening.